Yeah, this week is going to be about how to use LP to design algorithm, right? There's going to be two approach. Like today is going to be one approach called LP routing, which is in some sense like try to call LP as a black box, but do something between like before and after calling this black box. Next class on Thursday is going to be like just use LP as like just to help you design algorithm. There is no calling LP as a black box at all. Anyway, but I'm gonna introduce this technique using approximation algorithm. So let's recall. Again, the concept of approximation algorithm, right? Given any input, if we denote out of the input I by the value of the solution from the algorithm, and op I be the value of optimal solution, then we say that algorithm here is the alpha approximation algorithm. If for any input, it returns something that is almost as good as optimal solution up to factor alpha. And if the algorithm is randomized, then you just look at the expectation of the solution. Okay. Good. So let's look at one problem. Okay. Imagine that you have this map. This is Ann Arbor, and you want to maybe like put the fire station so that it cover every place in Ann Arbor. So this problem can be modeled as a graph problem like this, or like as a set problem like this, where you have first you have a universe. This is like a building or a building in Ann Arbor, like element 1 up to element n. Okay, and then there are sets. This is like the possible place that you can place the fire station. So each set is like each set Si is basically a subset of E. So Si basically kind of indicate which building it can cover. This building, this fire station can cover. Okay? And what we want to do is to find a smallest set cover. So choose a bunch of set from S here, I call it T, such that, so it's a set cover, meaning that the union of every set in our solution T here cover everything. Okay. So every element is covered by some set in T. That's what we want. Okay. Okay, this is like a set problem, but I usually like just to like get a picture of it. I usually write it in like graph like this, where you have a bunch of sets here. This is like S. This is E, the elements, and I just draw an edge here. If an element is in the set. Okay, so by drawing this edge, you basically get a bipartite graph. Okay. And the question of finding a set cover here is just to find like a choose nodes on the left here, so that every node on the right is a neighbor of some chosen node on the left. So these two nodes is a set cover, like form a set cover. Okay. So by the way, like this is actually like a generalization of a problem called a problem of vertex cover that you have seen, because you can imagine that like if each element here is contained in at most 2 sets, then actually it's a vertex cover problem. Can you see the correspondence, like what would this site correspond to in the vertex cover problem, and what would this site of nodes correspond to? suppose that each element is in at most 2 set, like, which is, yeah, like the degree of this guy is at most 2, not 3 like this.
When we did like vertex cover through max flow, or was or no, that was
no, there's no reduction here really, like. So basically you can think like this, like think like each element here is like an edge, each element correspond to an edge in the graph. Each edge has 2 endpoints. So like it will just connect to like two endpoint of an edge, right? So this side correspond to vertices, this side correspond to edges, and in the vertex cover problem we need to choose set of nodes such that it cover all edges. See? And we want to like in the vertex cover, we want to try like choose a small set of nodes, smallest sets of nodes. Here we want to find like a smallest family of sets. But yeah, but I hope you see the connection. Okay. So now, okay, there is a really simple greedy algorithm for this problem, which is just do the following. Just to do the following. Well, you look at your instance, and then just choose the best set. As in, choose one set S that cover most of the remaining elements. Like here, I can either choose S1 or S2 because it cover three guys. So I just gonna choose any one that cover the most. So I choose S1, and after that, I just throw out all elements that is covered. So I just throw away this guy. Now there are just 2 elements left. So next I just choose one set that cover the most of the remaining guys here, but each of the set just can cover just one element. You can just choose any one. Let's say choose this one. Remove the cover thing, and then repeat. Okay. So clearly this gives you a set cover. So we just need to ask like whether how good this is. And we see that this is not the best solution. The best solution could be 2, but this is like give you 3 sets. Yeah. Okay. Okay, let's see how bad it is. So here let's try to analyze it. So suppose that the optimal solution has size k. I claim that our solution will have size at most k log n. So it's not too bad up to log n factor. Okay. And the claim is this. The key lemma is this. So let's say that n0 denote the number of elements from the beginning, n, and ni denote the number of elements after the ith iteration. Yeah. Now, the claim is that the number of elements in the ith iteration actually is quite significantly smaller than the previous iteration. Okay. In other words, I'm going to say that like after the ith iteration, we would cover at least 1/k fraction of the previous iteration. So do you see why this should be true? It's not too hard though. Like the reason is just this. So you see that, like, let's say that okay, here is like, here is a set S, and let's say that here is like the remaining guys that is not covered yet, right? And we know that there are like k guys. Let's say this is the optimal one. The optimal one of size k, and the optimal solution will cover everyone here. It would cover everyone here. In fact, it would cover the whole thing. But in particular, it will just cover every remaining guys. Okay. So k elements can cover everyone here. So one of these k guys will cover at least n(i-1) over k elements.
But how do we know that the greedy algorithm is selecting one of the k elements that are in the optimal solution?
No, we don't know that. But we know that there exists a set that cover at least, there exists a set, like sum of the node exists set covering at least n(i-1) over k. But what greedy does is just to choose some set that cover the most of these guys. It can be in the optimal solution, it might not be, but it will cover at least this many elements. So it means that after the next iteration, the number of remaining elements will be shrink by this much, which means this thing. Questions?
Why is it guaranteed to cover that many?
Yes, this one?
Yeah.
Oh, because it's like if you have two elements, let's say let's say case 2, then like like you have like 10 guys here, then one of the two must cover at least 5. So if all of these guys cover strictly less than this, then it cannot cover this whole thing, right?
Just like pigeonhole principle. Right?
Yeah. Makes sense? Like it's like you have k guys, k sets. If you each of them cover even less than this, there's no way to cover everyone here. Yeah, so okay, there is a set that covers this much. So greedy choose the set that covers the most among this. So we will cover like at least this much too. Yeah. Okay. Everyone is good with this one? Okay. So now, once we know this, it means what? It means that how big can Ni be? Well, it's going to be at most 1 over k to the I times n0, which is n, right? But this is like basically less than minus e to the ik n. Yeah. Again, like note this inequality. This is just super useful. Like I use this always, like really often. When x it's like it's a inequality, but it's really accurate when x is small. Yeah.
Sorry, I still have a question. So I understand why we say on the first iteration, there must be a set that covers more than n(i-1) over k.
Mm-hmm.
But on future iterations, how is that? Because what if the optimal covering is we have like one, so there's 10 things in n(i-1, one of them covers 8, one of them covers 1, one of them covers 1. So if we take out the greedy algorithm takes out the A1, how do we know that that invariant will still be true on the next iteration? That's not clear to me.
So you don't think like you take away the one that you have already chosen. At any moment, okay, how do I say this? At any moment, you know that like suppose that you don't take away any set that you have chosen, and you just focus on the remaining nodes, the remaining elements here. You know that the X is the one that covered this much for sure.
Oh yeah, okay.
Yeah. And if the one that covered this much is the one that you already have chosen, then it's good. Make sense?
Yeah.
Right. Okay. Okay, good. So now, so Ni is this big. Ni is kind of getting smaller and smaller. So basically, once I is at least k ln n, maybe I just use the slides. So you know that Ni is this big. So if I is now look at the I like the iteration after k ln n iteration. Just from this inequality, you know that Ni must be less than 1. Because e to the minus k ln k over k here, this thing is just 1 over n, right? So this is now basically like a 1 when I is at least this. So after this iteration, Ni is less than 1, but Ni is an integer, so it must be just 0, meaning that you have covered everything. So now you get that like there are just this many iteration, k ln n iteration. So your solution must have size at most k ln n. Okay. So it means that this greedy algorithm is a deterministic ln n approximation algorithm. So it's a simple algorithm. Can we do this? Can we do better? Surprisingly, it turns out that it's not the case. Like if you can do a bit better, then P would be equals to NP. It's proven like more than 10 years ago. I actually don't know the proof. But it's about hardness of approximation. But maybe like Uyong, Nikhil would know the proof, but I don't. Okay. Just to make sure that you understand, maybe you can try this at home. Later in this today we look at weighted set cover algorithm, weighted set cover problem, and you can try at home that this greedy algorithm here would work even in the harder version of the problem, in the weighted version. Okay. But okay, let's look at the main thing today, which is LP routing. Okay. So we're gonna try to solve approximation algorithm using this approach, LP routing. And before I start, I need to tell you what is the word integer program. Integer program. What is this? When I say integer program, I just mean like it's just an LP where I force integrality constraint, similar to like a previous class. Okay. So, and by the way, note that like when you have an LP, we mentioned that we can solve this in poly time, but IP, integer program, is NP hard. You can try to solve, prove this. It's actually easy to prove, that is NP hard, because easily you can use it to model problem like 3Z. Actually, you can try this at home. Okay. But although it's NP hard, it's really nice for helping you designing algorithm. We'll see today. Okay. So and here is a template. Okay. The template similar it's like algorithmic paradigms like divide and conquer, dynamic program, and so on. Here's another paradigm. To approach any problem, you just first model the problem as an IP, and then after that just remove the integrity constraint from that IP and you get an LP. Okay. So we say that I denote an IP by pint, and after removing the integrity constraint, I call it P. So we use it, and there is this terminology. P is called LP relaxation of IP. Okay. Now, once you have an LP, you can solve it. We know that any LP can be solved. So solve that, and you get an optimal solution, optimal fractional solution of the LP. So you call it X star. So let's say that X star is an optimal fractional solution, right? Now that you don't have integrity constraint, this solution might not be integer. And after that, you just round the X star to the integral one in some way. This is a non-trivial part. Yeah, it's not that clear how to round it, but you need to design how to round the fractional one to the integral one called X hat. And that is a solution for your integer program. And we're gonna hope to say that after rounding X star to X hat, you get a good solution. Maybe not optimal, but quite good. So again, this is a algorithmic paradigm where you just start with integer program, relax it, you get a linear program, solve it, get X star, and then round it to get X hat. Okay, so let's try to implement this paradigm by one example. We're gonna look at weighted vertex cover problem. Okay. So yeah, this is the problem that you are by now familiar with. You have a graph, and now it has weights. Vertices have weights, and you want to find a vertex cover with minimum weights. The total weights here is minimized. Okay. In this picture, the optimal solution would be this blue set, because the weight is small and it cover every vertices, every edges. Okay. If it's unweighted, then you might just choose this guy and this guy, but here is weighted. Okay. All right. So let's try to solve this using LP routing. Okay. So the first step is to model the problem as an IP. Okay. So how do we do this? Basically, you just look at the output, the type of the output. The output is to choose a set of nodes, right? So you just think each node you have a choice whether to choose it or not. So then the variable then naturally should be something like for each node, you create a variable saying that you choose it or not. And then with this, what should be the objective? Yeah.
Minimizing the sum of xu times w of xu or whatever.
Yeah.
W.
Minimize the sum of xu times w. And this should be summing over all nodes, right? This is just a sum. This is really now like, it's just this thing. Yeah. The sum of the weights of everything that you choose. Make sense? And what should be the constraint? How can you write down the linear constraint?
Could it be
Yeah.
every edge is an equation and you need like
Every edge.
xu plus xv is greater than or equal to 1?
Exactly. Very good. Thanks. Yeah. With this, you can just say that, okay, for every edge, you must choose one of its endpoint. And this is an IP. So we're good. We are done with the first step. The next step is trivial. It's just to remove the inequality constraint. But when I remove it, I should do it like this. Like, I just say that instead of 0, 1, I just say that it's between 0 and 1. Right? Maybe I shouldn't, yeah. Okay. Yeah. Yep.
So then that's an additional constraint that all x values should be less than 1 and greater than 0.
Yeah.
Okay.
Yeah. So it used to be between either 0, 1. Now we just put basically the same thing, but it's not integer. Yeah. Okay. So that's basically the first two steps, right? Get an IP like this, and get an LP. Relax it. And the next step, you do nothing. You just solve, right? You assume that you can solve it. You get X star. Okay. And once you get X star may not be integer. Okay. So let me tell you how to round X star. Actually, any guess, but actually, you see, X star intuitively, okay, if it's it might be, let's say, it's 0.9 or 0.1. But if it's 0.9, then it kind of suggests that maybe you should choose that node because it's kind of close to 1. If it's really close to 0, maybe it's not really useful. That's the intuition. Yeah.
So maybe the rounding would be you start at the highest fractional ones, round those up to 1, and just keep doing that until you have a valid solution.
That's a totally valid one. Let me think if it works. That should work, yeah. But it's not the thing that I have in mind. Okay. So the thing that I have in mind is this. I just say that if it's more than half, choose it. If it's less than half, don't choose it. Okay. And yeah, the one that you return is just the one that you choose it, that you set to 1, that you round from half to 1. Okay. I think this will basically kind of your solution would be as good as this one because you look at the highest X star and you're gonna choose it, keep choosing that. And basically you might stop before, here I just choose everyone whose value is more than half, and you might stop like you might not choose some guys here that is like even if this is more than half. Yeah. But anyway, this is one simple way to route it. We just need to convince ourselves that first, this is actually a vertex cover. And second, it gives you somewhat good approximation. Okay. Anyone have an idea why this should be a vertex cover?
We have a constraint that for every edge, the sum of the values on each vertex should be greater than or equal to 1. So on every edge, there's guaranteed to be at least one node above 0.5.
Exactly. You have this one. The sum here is at least 1. There are 2 terms. So one of the term must be at least half. So you will basically cover every edge. Okay. And next is about approximation. So let's try to analyze it together. Okay. Okay. So first is a vertex cover. We're good. Okay. So next, I claim that this will give you 2 approximation. Okay. So let's see. The size of your solution, right? The size of your solution is just the sum of all nodes u, w, u times x hat u. Okay. Now, this is gonna be at most sum of every node 2 times x star u. This is at most 2 times x star u because you either round down, which is good, or you might round up. But when you round up by at most twice, at most double. Right? You round up the one that already more than half to 1. So it will not grow by more than 2 factor. So you get this. But what is this? This is exactly twice of the optimal value of the LP. Okay. But the optimal value of the LP is going to be at most 2 times of IP. Like, let's call P here. And this is at most P int. So this is like optimal solution of LP would be at most optimal solution of the IP, because yeah, this is a relaxation, right? And now what do we have? We have that the size of W, the weight of T here, is just at most twice the optimal integral solution. So it gives you 2 approximation. Make sense? Okay. So we want to prove, yeah. So like to say that it's 2 approximation, you just need to say that the algorithm, what algorithm return is as good as the optimal solution up to value of 2, up to a factor of 2. So here we're done. Okay. So I want to note down one thing that not that we are proving something stronger than 2 approximation, because this is what it means to say that it gives 2 approximation, but actually we prove that it's even at most 2 times LP value, and this is like a stronger, right? So what really happened is this: like you start with your problem. Integer problem, you relax it to LP. Now, after relaxation, the optimal value can go down, right? And then you solve like you get x star, which is like some fractional solution. Then you round it up to some x hat. And what we just bound is that we say that the value of x hat is not too big compared to x star by a factor of 2. So we bound this gap, actually that they are within a factor of 2. But like what we really need is just to bound this gap between of the IP and thus our integral solution. We need to bound this, but we do something stronger. And the reason that we do this is basically because like LP is something that we have solved, we can analyze it, it's easy to reason about. So all of this template, like our algorithm from this template, is always gonna do something stronger like this. We're gonna bound your optimal, like your solution with the optimal LP solution, not the IP solution. But it is good enough. Okay. So let's see another example.
I actually have a question.
Yep.
How do you know that val is gonna be greater than or equal to opt also? You're not gonna get tricked into something better?
So val of x star, you mean?
The rounded, sorry.
Oh, this one?
Yeah.
Oh, because it's some solution. This is some solution that is integer. So optimal solution by definition is just the minimum guy, minimum solution.
Anything that's valid, that's integer, okay.
Yeah, yeah. It's a valid solution, so it's at least this. Yeah. Okay. Okay, good. So that was like how to get. So you see that like basically kind of the first thing is just to model the problem, and then this is nothing, you do nothing here, and then you design this one. So it's mostly about designing routing algorithm. Okay, so previously it was deterministic routing, now we're gonna do it randomized. Okay, so let's look at the set cover again problem, but now it's weighted version. So it's just the same problem, but except that now you have cost on each set, and you want to find a set cover such that the total cost is minimized. Okay, so let's try to get an IP together again. What should be my variables? Like I should create a variable for each of what?
Whether each vertex is chosen also.
Yeah, vertices, which vertices, like
I think the construction would be the same, where on the left you have the sets, and on the right it would be the universe.
yeah.
And it'd be like a 1-0 variable, whether
1-0, yeah, I should, yeah, good. I wanna create a 0-1 variables for each what? For each of what?
Sets.
For each set, good. For each S in the set, like in the set S, I create XS, right? And that makes sense because we wanna choose a subset of the guys here. Okay. So what is the objective?
Minimize sum over XS.
Sum over XS. Not quite, but close. Something is missing.
Oh, is cost?
Exactly.
Just cost of the set times the indicator.
Yeah, exactly. So XS times the cost of S. Good. What's the constraint?
For each E, instead of having the sum of just two things, now we have the sum of every set, or like the indicator variables for every set that contains E.
Good.
Has
S
to be greater than or equal
contain
to
E.
1.
at least one. Yeah, exactly. So we just want to choose, we want that like for each element, one of the set that it contains it must be chosen. So this is just like a, to sum is like a to or, right? Like or like a sum of the set that contains E must be chosen. So this is an IP. That's it. We get the first step. And I just write down like this. And then relax it, just nothing. And then solve it. Okay. And then we need to round. Okay. If I tell you that I'm gonna round this thing in a randomized way, what do you think? Any suggestion?
And before we rounded up, like if it was 1/2 or not, like plus like above 1/2, and that's because there were two constraints, or like basically two things per edge, and now there's some arbitrary number of things per S. So I might think like if it's above like 1 over cardinality of S, it's kind of like type of thing. I don't know exactly.
Yeah, that would not be good because, for example, if for example like there are one element E1 and then like there are n sets, or yeah, there are many sets, I don't know, m, yeah, did I use m, yeah, m sets, and they all just can cover all of these things. It could be that each of the xs here equals 1/m. We know that the optimal solution have size 1. Here we're gonna like maybe choose everything. Yeah. So
Of those that are greater than or equal to 1/m, randomly choose them.
Yeah, that would work in this example. Okay. So let's consider like a sum. Like we want to try to, at least from this example, we want to choose something like one set, not like all. And okay, let's try to consider one algorithm that will not work quite yet, but it's close to work. Okay. I'm just gonna like think of x star as like suggestion, whether to choose it or not. X star of the set is between 0, 1. So I just think of this as a probability. And I just choose the set S if with this probability. Okay. Okay. So that's it. Like I just think of x star S as a hint how much we should choose it. Okay, let's try to analyze. It will not work yet though, but yeah. So first analyze the cost. Okay. So the cost is what? Expectation of the cost that we choose, of the thing that we choose, is then basically like a sum over all sets, right? The cost of this and the probability that we choose it. Or like it's just let me just write the probability that we choose it, that x hat s equals 1. This is the expectation of our cost. What is this?
X star S.
X star S. So this is then CS S star X. What is this?
Just the non-integral one?
Yeah, it's like a optimal LP value
Yeah.
of the LP. Right. It's just exactly this thing for X star. So it's the op value of LP, which is optimal value of IP. So you just see from here that like something is wrong because the cost is basically as good as optimal. So it shouldn't be true. Yeah. But okay. But let's bear with me. And now okay, so once we compute the cost, it looks like optimal solution, but don't forget we need to analyze that T is indeed a set cover too. That is a feasible solution. Right? Is it feasible? Almost. Why? Like basically for each of the element, we want to say that each element is covered. So let's analyze what is the probability that each element is covered. So the probability that E is not covered is E is not covered if none of the set that contains it is chosen. So it means that for each set that contains E, we don't choose it, but we don't choose it with this probability. And then how do we analyze this one? Again, once you see 1 minus something, use e to that thing, right? So this is just e to the minus x star s, and you do the product. So it's just the same as this product. It's just the same as a sum in the exponent. So you get this sum in the exponent. But this sum is a sum of all the set containing E of the sum of x star of all the set that containing E. This is at least 1. Right? Because x star is you know this thing. This is at least 1, so this is at most e to the minus 1. So each element is not covered with probably less than half. So you expect to cover each element by more than half probability. So it's kind of almost feasible, but not quite. Some element might not be covered. Yeah. Okay, some element may not be covered. There is a quick fix. If you choose some random set and you know that each element is not covered with at most half probability, how do you create how do you make sure that maybe any suggestion how to fix this?
This might be expensive, but you can just do it multiple times. Like if you find that you don't have a valid set cover, you just repeat the algorithm.
Exactly.
Just keep repeating until you have a valid one.
Good. Yeah, when you generate the first set, an element is not covered with probably less than half. Then if you do it twice, it will be not covered with probably at most 1/4, and again and again. So, if you, what should be the number of repetition so that we can say that each element is covered with high probability?
Some log n?
Log n, yeah. once you do log n, then this is like a e to the minus log n. So this is something like 1 over n, and you do union bar over n things. Yeah.
In this case, does n correspond to the amount of sets?
N is the number of elements.
Oh, okay.
So, okay. So this is a quick fix. Just generate log n independent copies of what we did, right? And return the union of those guys. Now, okay, the cost of the union is at most basically k times of p int, because each of them has cost in expectation at most of p int. So this is basically log n factor more. But now we know that like each element will not be covered with probability something like e to the minus k. K is like log n. So this is like basically e to the n over 100 or something. And now you do union bound over n elements. So now basically every element will be covered with high probability. Okay. So you will see many times like a factor of log n in the randomized algorithm, and many times log n just come naturally once you want something to hold with high probability. This trick of paying log n factor is just gonna be there again and again. Yeah. Okay, so this is log n approximation with high probability. And the cost, but note that the cost here is in expectation. But well, you can make it to hold with high probability easily. For example, by how? Like this is just in expectation. How do you get like the one that kind of at most log n times of like for sure, like with high probability? Yep.
Can you use Markov with whatever threshold you want?
Yeah, exactly. Yeah, let's say, yeah, this is like the expected cost here is like k times op. So with at least half probability, it's going to be at most 2k times opt. So, and then if you maybe now like try log n round of your, like just run your algorithm, this whole thing log n times, one of them will have will have cost at most 2k times opt, because each of them is good with probability half. Yeah. Okay. Good. So this kind of basic trick is something that you should internalize, right? Yeah. Like how to convert expectation to high probability, how to fix this, like how to fix this thing to cover every element. Yeah. Okay, so good. Let's look at another problem. Here's a new problem. It's a problem where you have a graph and you have k pairs, Si, Ti. Okay. And what you want to choose is to choose a path, Pi, that connects Si to Ti. So choose k many paths. So like the idea is like you have a graph, you have S1, T1, S2, T2, and so on, and you need to choose the path. Okay. And what do we want to minimize? We want that we want to minimize congestion. That is, each edge shouldn't be used too many times. Like we said that the congestion of an edge is just the number of times that an edge is in the path. And we want to minimize the maximum congestion of our edges. Okay. This is used a lot in like I don't know now is it used now, but like it was used for sure for circuit design. Like in circuit design, you kind of need to say that okay, this point need to go to this point, this point need to go to this point, and like you need to connect the wire somehow. But at any place, you don't want to have capacity to be too big. Yeah. Okay. But we're gonna think of this as a graph problem because it's a good abstraction. Okay. And by the way, you can think of this as some kind of flow problem too, right? It's like you have source and sink. You want to send one unit of flow from the first source to first sink, another unit of flow from another source to sink, and like the total flow value on any edge should be small. Think like you can think like that. Okay, so now it's harder to come up with the IP, but let's try. Okay. Let's say that PI is like a set of all SITI paths. Okay. I'm just gonna start for you by saying that like just for each path in PI for all I equals 1 up to k. Let's say that I just create this variable whether I choose this path or not. Now, what would be the constraint? What would be the constraint which says that I need to connect like from SI to TI?
What is XP again? Sorry.
PI is a set of all SITI paths. So like for all this is SITI. Oh shoot. What? No. Okay. Like this is one path. This is another path. This is another path. All these are in the set PI.
And what is XP?
XP is to say that I choose this path or not. It's like a variable saying that whether I choose this whole path to connect SI to TI or not.
So I guess it would be, the constraint would be the sum of all XP is equal to 1 because you're only picking one path.
Mm-hmm. Good. Yeah. So for all I, from 1 to k, this is sum over what? Sum over PI. This is just to say that we're gonna pick one path. Okay. But we need to minimize the congestion. What else? Like how should we model this? Can you like how can you express the congestion of an edge first of all? Let's say for each edge. For each edge, E, we need to express the congestion of an edge somehow.
So it'd be like the sum over all paths that contain that edge.
Yeah, the sum of all paths that contains that edge. Yeah, this is like basically the congestion of this edge. Okay. How do we like how do we minimize? Like right now we want to minimize the max overall age of this thing. And but that is not LP, right? So how do we do this? So here's a trick. There's nothing that stops you from putting the variables here. Suppose that you want to put the variables here, then yeah, tell me how to complete this.
Put a variable there, and then you're just minimizing that variable.
Exactly, just that.
Like wires.
That's it, yeah. That now you get an IP. Okay, good. So this is an IP, right? And then we can try to solve, like this is an IP, then you follow the template, relax it, and then solve it. There is a caveat though. How can you solve this LP? Because this LP has exponential size. Like the number of variables here is exponentially many. Okay. However, once you see this, you can actually think like this is where the intuition that I mentioned that this is like flow problem is helpful, because here's really just like you want to send one flow for like from Si to Ti for all I, and the total capacity, like the total flow value on each edge is bounded. Okay, and like so let's see if this makes sense. I claim that this is just, you can just write down another LP here that is now of polynomial size. It's just the same, like it's equivalent to this one in the sense that once you get the flow solution here, you can extract the set of paths here. Okay, so let's go through this a bit, right? What is this LP? This is an LP which says that I have the flow value on each edge. Flow I on HE is some number, right? And here I want that I want to send out one flow value, like out of Si. I want to send out one flow value. And then I have the flow conservation constraint like before, like in flow algorithm, like in flow problem. This is just to say that for every node that is not sort and sink, you have flow conservation. And then here I have that the total flow value on each edge, summing over all I, like the flow 1 of HE plus the flow 2 on HE plus up to flow K on HE. This is at most C. Right. And then the flow value need to be non-negative. Okay. So, and what we want to minimize? We want to minimize the congestion. Okay. So, first of all, does it at least intuitively, like, is it intuitive to you that this problem kind of describe the same problem here? Yeah.
I think so. What I don't understand is how we're going from sort of like multiple sources, multiple sinks to like single source, single sink. In
No, there is no single source, single sink. We have SITI. I want that for every I send type I flow of value 1 from SI. Like there are like K commodity, like K type of water. And I want to send 1 unit of type I flow from SI. I have the conservation constraint for each type of the flow. Like for each I here, I have flow conservation constraint. But now when it's about capacity constraint, this is like a summing of overall types. Yeah. So basically we're gonna send one unit of flow from SI to TI. But you know that because flow is just by flow path decomposition that we have seen last time. Given the flow, you can just decompose it into set of paths. Given the flow type I flow, you can actually decompose it into set of SITI paths that correspond to that flow with the same value. So, given flow I, you just get a set of paths from SI to TI. How much do you send flow for each path here? Question about this? What I need is that you should be convinced that given the solution here, you can construct the solution here, and given the solution here, you can construct the solution here too. And this direction is not too hard, right? Suppose that I choose a path from a P1 and P2 and maybe P3 like this. And this is one is value 0.1, one is value 0.2, another one is value 0.3. If you sum up the value of this path, it just gives you the SITI flow. It just comes to the you can assign the value of a FI just by summing the value of the path on each edge. And the capacity will be respected. The flow conservation constraint will be respected too, because you sum over the path. The path is a kind of conserve the flow. And you're gonna send one flow. So given the solution here, you can get a solution here. Given the solution here, you can get a solution here too. Because by using their first search thing to decompose flow into path with the same value. Make sense?
After LP, what would be the return value? What would you know afterwards?
Say again?
What would be the return value?
The return value?
What would you know after you did each of them?
The return value is just this thing, right? This is the objective.
Yeah.
But sorry, I don't quite get the.
Oh, you're talking about how if you know left side, you can go to the right, or if you know the right side, you can go to the left. What does that mean?
Oh, I mean that.
What would we know? After writing it,
Oh, it means that the two formulation must have first of all the same optimal value, because you can convert the two solution to each other.
Okay. Yeah.
Yeah.
Okay.
And so if I want to solve this problem optimally, it's enough to solve this problem optimally and then get the optimal solution there.
Yeah.
Yeah. More questions? This is kind of quite non-trivial, but yeah. But yeah, okay. So it means what? we get the equivalent LP with polynomial size. This is the LP P prime. It's of polynomial size. We can solve it and then extract the optimal solution for this one using flow path decomposition. Okay. So now, okay. Now basically we can solve for X star. How to route it? So let's say that I like like a natural way again is just to solve to choose a path P with probability X star P. It might not give me the feasible solution. This might not work. Why? Yeah.
For the same reason as before.
Like for the same reason as before. Yeah. But now can we fix it with the same way like before? Not quite, because it's really like for every SIPI, like for every pair, demand pair, we want to choose exactly one path. Right? We want to choose exactly one path. You don't want to say like, okay, maybe like each pair you don't cover it with some probability, so let's try like log n times. That might give you log n pairs, log n paths. But now we want to choose exactly one path. Okay. And okay, there is another natural way to do this. Suggestion.
And we're still using randomness here.
Yeah.
Could you do something where you choose the one with the highest probability and remove it, and then look at the others? I don't know.
I don't think that will work. I cannot say why yet. So here is the okay. Basically, you can think like this, like you just feel like the XP for overall like a overall PI, overall path from like for the demand I. This guy you can view it as a probability distribution. Why? Because for every path here is between 0 1, and the sum of this is exactly 1. Right? From here, the sum is exactly 1. So this is like a distribution. So you can just think of this as a distribution among all paths for the demand I. So you just choose one path according to the distribution here. So just pick one path according to this distribution. So with this, you're going to just choose exactly one path for each pair. So it's feasible solution. Just need to bound the congestion. Just need to bound the quality of it now. Right. So are you with me? You're good? Okay. All right. So now it's about bounding the congestion. So let's say that YE is the congestion of E, which is just like I just count for each pair whether the path that we choose for pair I contains E or not. That's the congestion of HE, right? And we want to bound this thing, the maximum congestion. Okay. So how do we do this? Well, I just gonna create some indicator. Let's say that x e for the demand pair I is indicate whether e is in the path that we choose for demand pair I, and then ye is just a sum over I of xie. Okay, and we want to bound this ye. So basically, you see that ye is like a sum of 0, 1 independent random variables. Because it's a sum over all I, and for each I we do it. For each demand pair we choose things independently. So this is a sum of 0, 1 independent random variables. So once you see this, to analyze this, you basically try to apply Chernoff, right? Because Chernoff is good for this type of variables when it's a sum of 0, 1 independent things. Okay. Try to apply Chernoff, then you do union bound over all H. That's the approach. But to apply Chernoff, we need to know the expectation first, right? So let's try to compute the expectation. What the expectation of ye? Maybe I do this first. Ye is just a sum over I, right? Indicator that E is in P hat I. Okay. How do we analyze this? This is sum over all H. And whether E is in the P hat I is just we basically sum over all P in Pi, and then over all P that contains E, indicator that E is in P. And this is just this sum here. It's just sum of really just is the same as sum of all P, indicator of E in P. So now you can just say that the expectation of ye is just sum over PE, P that contains E, and the expectation of this thing. So it's just a variable, like probability that that E is in P. What is this?
Expected value of an indicator variable. It's probability.
Yeah, it's really just X star P, right? It's from the, like we choose the edge, we choose the path P with this probability exactly. So then like this can be bound by just of the LP, right? We know that like for every edge, this is like just a congestion of an edge in the LP, the fractional congestion. The fractional congestion is just at most of LP. Okay. Oh, I'm a bit over time. So now you get that ye is a sum 0, 1 independent variables, sum of 0, 1 independent random variables. The expectation is at most of LP. Now, like with like application of Chernoff bound, you can just say that like it shouldn't deviate from expectation by more than log n factor with high probability. Just maybe just try to do Chernoff bound. You can get that. Yeah, like the rule of thumb is that once you can use Chernoff bound, it cannot deviate from what you expect by log n with high probability. Try to do this. You can do this at home. But once I know this, I also actually know that it's at most 1, max of 1, and of LP. I need to be a bit careful here. But we know that max of 1 and of LP is at most of IP. Just because, yeah, of IP is more than 1 for sure because congestion is at most 1 trivially. But and of IP is more than of LP because LP is relaxation. Okay. So with this, we can get that like max congestion is at most 30 log n times of IP. So it is now like a log n approximation. Okay. Just to make sure you understand, you can try this at home. That if actually you know that the optimal LP value is something like log n, you can actually in this case get 1 plus epsilon approximation. Just follow the same analysis and try this. Okay. Just let me wrap up now. So we learned like a 2 strategy for approximation algorithm today. One is just greedy, a simple thing, but I want to stress on this template. It's like it's an LP routing template, which is first relax, get the IP, relax it, solve it, and route it. Okay. It's just really powerful and you can use it to many problems. Okay. Next class will be another approach. It's called primal dual approach. Yeah, you see what it is. Yeah, see ya.